Now, in this lecture, we will find the radius of the small circle. In the drawing, we have a quarter circle, and we know that angle BCD equals to 90 degrees. This angle equals to 90 degrees. We also know that chord CD equals to 2 units and OD equals to 3 units. Actually, OD is the radius of the quarter circle, so I will mark it as capital R. And also, in a quarter circle, angle DOB is a right angle. It equals to 90 degrees. And inside the quarter circle, we have a small circle, and we want to find out the radius of this small circle. So first of all, we will define the center of the small circle as P, and then we will join together points A and P by a straight line. Actually, AP is the radius of the small circle, so I will mark it as small r. AP is the radius of the small circle because of the fact that line segment AP starts from the center of the circle and ends at point A, that is a point on the small circle itself. So AP is the radius of the small circle, and actually BA, line segment BA is tangent to the small circle at point A. So we have a rule that if you have a circle this is the center of the circle, and we have radius of this circle. This is the radius of the circle, and if we have here tangent to this circle at point M, then the tangent to the circle is perpendicular to the radius. That is to say, this angle equals to 90 degrees, because the radius is perpendicular to its tangent. That is to say, this angle equals to 90 degrees. So actually, we have here tangent AB to the small circle. AB is tangent to the small circle at point A, and we have the radius AP. So according to the rule that radius and tangent are perpendicular to each other, this angle equals to 90 degrees. Okay? In the next step, we will join together points P and B by a straight line. And the triangle APB is a right triangle because of the fact that angle PAB is a right angle. Okay, and we will define angle ABP as theta. So tangents theta will be equal to AP over AB. Okay, tangents theta equals to AP over AB, and we know that AP is the radius of the small circle, so we can substitute AP by R. And if we multiply this equality by AB, we will get that the radius of the small circle equals to AB times tangents theta. Okay, so in order to find out the radius of the small circle, we have to find out the value of AB and the value of tangents theta. Okay, so in the next step, we will define the touching point between line segment CB. We define the touching point between line segment CB and the small circle as point X. Actually, line segment CB is tangent to the small circle at point X. Then we will join together points P and X by a straight line. Actually, PX is also the radius of the small circle. We'll mark it as R because of the fact that PX starts from the center of the small circle and ends at point X, that is a point on the small circle itself. Therefore, PX is the radius of the small circle. In the next step, I will prove that triangles APB and triangle PBX are congruent to each other. So I will draw those two triangles again. So I drew triangle APB and triangle PBX again, we know that AP is the radius of the small circle, it equals to small r, and PX is also the radius of the small circle. Okay, so we can see from the drawing that AP equals to PX, AP equals to PX, both those line segments are the radiuses of the small circle. Okay, so AP equals to PX, and both those two line segments are the radiuses of the small circle, therefore they are equal to each other. And also PB is a common side. Side PB belongs to triangle APB, and it is also belongs to triangle PBX. So PB equals to PB. It's a common side. It belongs to both triangles. Okay, PB equals to PB, and actually AB equals to BX. AB equals to BX. AB equals to BX according to two tangents theorem. Two tangents theorem. Actually, two tangents theorem states that the lengths of two tangents from common external point to a circle are equal. So I will read two tangents theorem again. Two tangents theorem states that the lengths of two tangents from common external point to a circle are equal. So actually, according to two tangents theorem, if you draw from external points, that is to say from, in this example, from point B, two tangents to the circle, then the length of those two tangents are equal. That is to say, AB equals to BX. Again, if you draw from an external point of the circle, that is to say from point B, two tangents to the circle, then the length of those two tangents are equal. That is to say AB equals to BX. So actually we proved that all the sides of triangle APB are congruent to all the sides of triangle PBX. Therefore, triangle APB is congruent to triangle PBX according to side rule. Okay, so I will read again the things that I wrote. Triangle APB is congruent to triangle PBX according to side rule. Actually, when you prove that one triangle has three sides that are congruent to another triangle, then those two triangles congruent to each other according to side rule. Okay, so those two triangles congruent to each other according to side rule. So from the fact that triangle APB congruent to triangle PBX, we can conclude that angle ABB that equals to theta equals to angle PBX. Okay, angle ABB equals to angle PBX. So angle ABP equals to theta. So if angle APB equals to theta, then angle PBX will be also equal to theta. Okay. So again, angle ABP equals to angle PBX according to the rule that corresponding angles in congruent triangles are equal to each other. Corresponding angles in congruent triangles are equal to each other. Okay. Again, corresponding angles in congruent triangles are equal to each other. Triangle APB congruent to triangle PBX, therefore the corresponding angles, angle ABP and angle PBX are equal to each other. Okay. So in the next step, we will extend line segment CB and the radius DO until they intersect with each other. Okay, so we will extend CB and DO until they intersect each other at point E. Point E is the intersection point between CB and DO. Okay, so by extending those two line segments, we created here two vertex angles. Angle EBO, angle EBO and angle ABC are two vertex angles. Again, angle EBO and angle ABC are two vertex angles. So I will draw them again in order to make it clear. Okay, so we have angle so actually the two angles that I marked in a red line are two vertex angles. Angle ABC, this angle, and angle EBO, this angle, are two vertex angles. And we have a rule that states that vertex angles are equal to each other. Again, the rule states that vertex angles are equal to each other. Okay, so actually, according to this rule, angle ABC, this angle, equals to angle EBO. Because of the fact that there are two vertex angles and vertex angles are equal to each other. Okay, but what is the value of angle ABC? From this drawing, we can see that angle ABC equals to theta plus theta, that is to say angle ABC equals to 2 theta. Okay, angle ABC equals to 2 theta, and from this equality we can derive that angle EBO also equals to theta. So this angle EBO equals to 2 theta. Okay, and actually it is given us in the question that angle BCD is a right angle, it equals to 90 degrees. Therefore, angle ECD is also equals to 90 degrees, because we continued CB, we extended CB, so we didn't change the size of angle BCD, so angle ECD equals to 90 degrees. This angle ECD equals to 90 degrees. And actually angle ECD that equals to 90 degrees is a peripheral angle. Again, this angle ECD is a peripheral angle, because of the fact that it is located inside the quarter circle, so it is a peripheral angle. Again, so angle ECD that equals to 90 degrees is a peripheral angle. And we have a rule that states that any peripheral angle that equals to 90 degrees rests on the diameter of the circle. So I will read the rule again. The rule states that any peripheral angle that equals to 90 degrees rests on the diameter of the circle. So actually, peripheral angle ECD equals to 90 degrees. Therefore, according to the rule that I read, peripheral angle ECD rests on the diameter of the circle. We know that peripheral angle ECD rests on ED, so ED is the diameter of the quarter circle. So according to the rule that I stated, ED is the diameter of the quarter circle. Okay, ED is the diameter of the quarter circle. We know that the diameter of any circle or quarter circle equals to 2 times the radius of the circle. So actually ED equals to 2 times the radius of the quarter circle, 2 times capital R. And if OD equals to R, then OE must be also equal to R in order to complete the size of ED to 2R, okay? So R equals to 3 units, so OE also equals to the radius of the quarter circle. So here we will complete the quarter circle to a semicircle. So actually we know that DE or ED is the same, is the diameter of the quarter circle, or it is also the diameter of the semicircle. Therefore, ED as the diameter is also a straight line. Okay, so ED is a straight line. ED or DE is a straight line. Okay, DE is a straight line because of the fact that is the diameter of the semicircle. Okay, DE is a straight line, and we have a rule that states that the sum of the angles on a straight line equals to 180 degrees. Again, the sum of the angles on a straight line equals to 180 degrees. Okay, the sum of the angles on a straight line equals to 180 degrees. And especially because of the fact that ED is a straight line, then the sum of the angles on a straight line ED at point O must be equal to 180 degrees. So what we have at point O we have here 90 degrees plus the size of angle EOD. This angle must be equal to 180 degrees according to the rule that is stated. 90 degrees plus angle EOD must be equal to 180 degrees. So here we will subtract 90 degrees from this equality, and we will get that the size of angle EOD equals to 180 degrees minus 90 degrees is 90 degrees. So actually this angle EOD, is a right angle. Okay, and because of the fact that angle EOD is a right angle, then we can conclude that triangle EOB is a right triangle because it has one angle that equals to 90 degrees. Okay, so we will focus on the right triangle, triangle EOB. So in the right triangle, triangle EOB, we know that the sum of the angles is equal to 180 degrees. So 90 degrees plus 2 theta plus the size of this angle, that is angle OEB, must be equal to 180 degrees because of the fact that the sum of the angles in any triangle equals to 180 degrees. And especially in triangle EOB, the sum of the angles is equal to 180 degrees. So 90 degrees plus 2 theta plus the size of angle OEB equals to 180 degrees. So here we will subtract 90 degrees from this equality, and we will get that 2 theta plus angle OEB will be equal to 180 degrees minus 90 degrees is 90 degrees. Okay, so here we will subtract 2 theta from this equality, and we will get that angle OEB equals to 90 degrees minus 2 theta. Okay, so this angle OEB equals to 90 degrees minus 2 theta. Okay, in the next step we will focus on the right triangle DCE. Okay, so in the right triangle DCE, the right big triangle in triangle DCE, we know that the sum of the angles is equal to 180 degrees. So the size of angle EDC, this angle, plus this angle that equals to 90 degrees, plus this angle that equals to 90 degrees minus 2 theta must be equal to 180 degrees. Again, in the right triangle DCE, the sum of the angles is equal to 180 degrees. Okay, so here we have 90 degrees plus 90 degrees is 180 degrees in this side of the equality, and we have 180 degrees on the other side of the equality, so we can cancel 180 degrees because we have them on both sides of the equality. Okay, so here we left only with 0, and what is left after we cancelled 180 degrees on the other side of the equality is angle EDC minus 2 theta equals to 0. Okay, so here we will add 2 theta to this equality, and we will get that angle EDC equals to 2 theta. Okay, angle EDC equals to 2 theta. So this angle equals to 2 theta. Okay, so we will continue to focus on the right triangle ECD. On the right triangle ECD, we know according to the Pythagorean theorem the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So CD square plus CE square equals to DE square. Again, CD square plus CE square equals to DE square. Again, in the right triangle CDE, according to the Pythagoras theorem, CD square plus CE square equals to DE square. But what is the value of CD? CD equals to 2 units. It is given us in the question. So CD square is 2 square, 2 square is 4, plus CE square equals to DE square. What is the value of DE? DE is the diameter of the semicircle. So it equals to 2R, and R equals to 3 units, so 2 times 3 is 6, so DE equals to 6. And DE square is 6 squared, 6 squared is 36. So in total we got that 4 plus CE square equals to 36. Here we will subtract 4 from this equality, and we will get that CE square equals to 36 minus 4 is 32. CE square equals to 32. Here we will take a root out of this equality, and we will get that CE equals to the root of 32, but 32 equals to 16 times 2, and the root of 16 is 4. So in total we got that CE equals to 4 times root 2. Okay, CE equals to 4 times root 2. So actually we'll continue to focus on triangle CDE. In triangle CDE, tangents 2 theta tangents 2 theta in triangle CDE, the right triangle CDE, will be equal to CE over CD. Again, in the right triangle CDE, tangents 2 theta equals to CE over CD. But what is the value of CE? CE equals to 4 times root 2. Okay? 4 times root 2. And what is the value of CD? CD equals to 2 units. It is given us in the question. So in total we got that tangents 2 theta equals to 4 times root 2 over 2. 4 over 2 is 2. So in total we got that tangents 2 theta equals to 2 times root 2. Okay, tangents 2 theta equals to tangents 2 theta equals to 2 times root 2. And we want to find out the radius of the small circle. We know that the radius of the small circle equals to AB times tangent theta. And we found out only the value of tangent 2 theta, so in order to find the value of tangent theta from tangent 2 theta, I will present to you a new trigonometric identity that can help us to find out the value of tangent theta from tangent 2 theta. Actually, the trigonometric identity states that the value of tangent 2 theta is actually equals to 2 tangent theta over 1 minus tangent square theta. Okay? So, we have already found out that the value of tangent 2 theta equals to 2 times root 2. So we can substitute tangent 2 theta in the trigonometric identity by 2 times root 2. And here we have 2 tangent theta over 1 minus tangent square theta. Okay? So here we will define tangent theta as x. So tangent theta equals to x according to our definition, and we will substitute tangent theta by x in this equality, and we will get that two times root 2 equals to 2 tangent theta is 2x over 1 minus tangent square theta is minus x squared. Okay, so we got this equality. That 2 times root 2 equals to 2x over 1 minus x squared. Here we will multiply this equality by 1 minus x squared, and we will get that two times root 2 times 1 minus x squared equals to 2x. So here we will divide this equality by 2, and we will get that root 2 times 1 minus x squared equals to 2x over 2 is x. So here we will open the brackets in this side of the equality, and we will get that root 2 minus root 2 x squared equals to x. So here we will add root 2 x squared to this equality, and we will get that root 2 equals to root 2 x squared plus x. Here we will subtract root 2 from this equality, and we will get quadratic equation that root 2 x squared plus x minus root 2 equals to 0. Okay, so we have here quadratic equation. Actually, the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. So that is the general formula for a quadratic equation when a, b, and c are the coefficients of the quadratic equation, and x is the variable that we want to find out. And we will find out the value of x according to the following new formula, the following formula. The value of x equals to minus b plus minus root of b squared minus 4 times a times c over 2 times a, when a, b, and c are the coefficients of the quadratic equation, and x is the variable that we want to find out. So in our specific quadratic equation, root 2 x squared plus x minus root 2 equals to 0, here the coefficients of this quadratic equation is a equals to root 2, b equals to 1, and c equals to minus root 2. Okay, so we will substitute a, b, and c in this formula by the values for a, b, c in our specific quadratic equation, and we will find out the value of x that is actually equals to tangent theta according to our definition. So in our specific quadratic equation, x will be equal to minus b equals to 1, so minus b is minus 1 plus minus root of b squared. B is 1, so b squared is 1 square, 1 square is 1, minus 4 times a is root 2, times c is minus root 2, over 2 times a, that is 2 times root 2. Okay, so x equals to x equals to minus 1 plus minus, here minus times minus is plus, and root 2 times root 2 is 2, and 2 times 4 is 8, and 8 plus 1 is 9. So in the root we have left only with 9 over 2a is 2 times root 2. So in total we got that x equals to minus 1 plus minus root 9 over 2 times root 2. The root of 9 is 3, so I write it down. X equals to minus 1 plus minus root of 9 is 3 over 2 times root 2. So we have here two solutions for x. The first solution is that x equals to minus 1 minus 3 over 2 times root 2. Minus 1 minus 3 is minus 4. Over 2 times root 2. So minus 4 over 2 is minus 2 over root 2. So we actually found out that x equals to minus 2 over root 2 is negative number, is smaller than 0, it is a negative number. And actually we add here right triangle with angle theta. So in the right triangle APB, we know that theta plus angle APB must be equal to 90 degrees. Theta plus angle APB must be equal to 90 degrees. So theta equals to 90 degrees minus angle APB at 90 degrees minus angle APB is actually less than 90 degrees. So theta is less than 90 degrees. And if theta is less than 90 degrees, is smaller than 90 degrees, then again, if theta is smaller than 90 degrees, then tangent theta, x that equals to tangent theta, must be a positive number. It must be greater than 0. But we found out that x that equals to tangent theta equals to minus 2 over root 2, that is negative number. We found out that x equals is a negative number, while x must be a positive number, Therefore, this is incorrect answer, and we only left with the possibility that x equals to minus 1 plus 3 over 2 times root 2. So it equals to minus 1 plus 3 is 2, and 2 over 2 times root 2 is actually 1 over root 2. X equals to 1 over root 2, and x equals to tangent theta according to our definition. So tangent theta equals to 1 over root 2. Okay, so we found out that tangent theta equals to 1 over root 2, and we have already found out that tangent to theta equals to 2 times root 2. Okay, and as you should remember, the radius of the small circle equals to AB times tangent theta. So we have already found out that tangent theta equals to 1 over root 2, so the only thing that is left to find is the value of AB. Okay, so in the next step we will focus on triangle EBO, on the right triangle EBO. So on triangle EBO, tangents to theta, this triangle, tangents to theta equals to OE over OB. Okay, in the right triangle OBE and triangle EBO, tangents to theta equals to OE over OB. But what is the value of OE? OE equals to 3 units. So it is 3 over OB. So we got that tangents to theta equals to 3 over OB. Okay? But we have already found out that tangents to theta equals to 2 times root 2, so we can substitute tangents to theta by 2 times root 2. Okay? We will get that tangents to theta, that is 2 times root 2, equals to 3 over OB. So we got that 2 times root 2 equals to 3 over OB. Here we will multiply this equality by OB, and then we will divide it by 2 times root 2, and we will get that the value of OB is equals to 3 over 2 times root 2. Okay, so we found out that the value of OB equals to 3 over 2 times root 2. Okay, OB equals to 3 over 2 times root 2. In the next step, we will join together points P and O by straight line. So actually, triangle APO is a right triangle because angle OAP is a right angle. In the next step, we will extend the hypotenuse OP until it touches the two circles at point M. We extended the hypotenuse OP until it touches the two circles at point M. Actually, point M is the touching point of the small circle with the big circle, and it is actually the where OP is after it is actually MO is also the radius of the semicircle. So MP is the radius of the small circle, MP equals to small r, and MO equals to capital R, because MO is the radius of the semicircle. MO is the radius of the semicircle because of the fact that it starts from the center of the semicircle, that is to say from point O, and ends at point M, that is a point on the semicircle itself. Therefore, MO is the radius of the semicircle. And what is the value of PO? PO, the hypotenuse of triangle APO. PO, from the drawing, you can see that PO equals to MO minus MP. Again, PO equals to MO minus MP. Okay? PO equals to MO minus MP. But we have already found out that MO is the radius of the semicircle and MP is the radius of the small circle. So we can write down that PO equals to capital R minus small r. And we know that capital R, the radius of the semicircle, equals to 3 units. So actually PO equals to 3 minus R. PO equals to 3 minus R. So actually in the right triangle APO, we know that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AP square plus AO square equals to PO square. Again, in the right triangle, triangle APO, according to the Pythagoras theorem, AP square plus AO square equals to PO square. But what is the value of AP? AP, from the domain you can see that AP equals to small r. AP equals to small r. So AP square is small r square plus AO square equals to PO square. We have already found out that PO equals to 3 minus r, so PO square is 3 minus r square. So in total we got that r square plus AO square equals to 3 minus r square. Here we will open the brackets in this side of the equality, and we will get that r square plus AO square equals to 3 minus r square is 9 plus r square minus 6r. So here we have r square in this side of the equality, and we have r square on the other side of the equality, so r square will get cancelled, and what is left after we cancelled r square is AO square equals to 9 minus 6r. So here we will take a root out of this equality, and we will get that AO equals to the root of 9 minus 6r. So we found out the value of AO. We found out the value of AO, and we have already found out the value of BO. BO equals to 3 over 2 times root 2. BO equals to 3 over 2 times root 2. Okay? And what is the value of AB? AB equals to AO minus BO. Again, AB equals to AO minus BO. Okay? AB equals to AO minus BO. But we have already found out that the value of AO is root 9 minus 6r, and the value of BO is 3 over 2 times root 2. So we can substitute AO by its value, and we will substitute BO by the value that we found for BO. So AB will be equal to AO, and AO is the root of 9 minus 6r minus BO. BO equals to 3 over 2 times root 2. Okay, so that is the value of AB. And we have already found out that the value of tangent theta is actually 1 over root 2 and the radius of the small circle equals to AB times tangent theta. And we actually have both the value of AB and also the value of tangent theta, so the only thing that is left to do is to substitute AB by its value and to substitute tangent theta by 1 over root 2. So we'll do it now and we will get that R equals to AB. AB is the root of 9 minus 6R minus 3 over 2 times root 2 times tangent theta. Tangent theta is 1 over root 2. Okay, so we got this equality that R equals to the root of 9 minus 6R minus 3 over 2 times root 2 times 1 over root 2. Here we will multiply this equality, by root 2 and we will get that root 2 times R equals to the root of 9 minus 6R minus 3 over 2 times root 2. Okay. So here we will add to this equality 3 over 2 times root 2 and we will get that 3 times 2 times root 2 plus root 2 R equals to the root of 9 minus 6R. Okay, so here we will multiply root 2 times R by 2 times root 2 and then we will divide it by root 2 times root 2 in order to have a common factor with this expression. We will get that 3 over 2 times root 2 plus root 2 times R times 2 times root 2 equals to the root of 9 minus 6R. So we'll get here that 3 over root 2 times root 2 is 2 and 2 times 2 is 4. So in total we got here 4R over 2 times root 2 equals to the root of 9 minus 6R. Okay, so here we will square this equality and we will get that 3 plus 4R squared over 2 times root 2 squared is 8 equals to the square of the root actually the square cancels the root. So when we square this expression, we actually cancel the root, because the square and the root are two opposite functions. So if you do the square and then the root, you actually did nothing, because one cancels the other. So the square of the root is actually cancel each other, so we only left with 9 minus 6r. So here we will multiply this equality by 8, and we will get that 3 plus 4r squared equals to 8 times 9 is 72, and 8 times minus 6r is minus 48. Minus 48r. So here we will open the brackets in this side of the equality, and we will get that 9 plus 16r squared plus 3 times 4r is 12r, and 12r times 2 is 24r, equals to 72 minus 48r. Okay, so here we will add 48r to this equality, and we will get that 6r squared plus 9, 24 plus 48 is 72, here we will subtract 72 from this equality, and we will get that 16r squared plus 72r minus 63 equals to 0. Okay, so here we have a quadratic equation. We know that the coefficients of the quadratic equation are a equals to 16, b equals to 72, and c equals to minus 63, and the solution for a quadratic equation is actually x equals to minus b plus minus root of b squared minus 4 times a times c over 2a. And in our specific quadratic equation, the variable is r, so x equals to r. So r equals to minus b, b is 72, so minus b is minus 72, plus minus the root of b squared is 72 squared is 5,184, minus 4 times a is minus 64 times minus 63 is 4032 over 2a is 2 times 16 is 32. So in total we got that r equals to minus 72 plus minus 5184 plus 4032 is 9216 over 32. So in total we got that the radius of the semicircle equals to minus 72 plus minus, and the root of 9216 is 96 over 2. So we actually have here two solutions to this quadratic equation, or two values for the radius of the small circle. The first solution is r equals to minus 72 minus 96 over 32. Minus 72 minus 96 is minus 168 over 32. It equals to minus 5.25. So the radius that we got is a negative, but the radius of a circle must be a positive number, so this solution is incorrect. So we left only with the other solution, that r equals to minus 72 plus 96 over 32. Minus 72 plus 96 is 24, and 24 over 32 is 3 over 4, or 0.75. So the radius of the small circle equals to 3 over 4 units, or 0.75 units. Again, the radius of this small circle equals to 3 over 4 units, or 0.75 units. Okay, so now I will summarize the lecture. Actually, we wanted to find out the radius of the small circle, and the small circle is inside a quarter circle. Therefore, we know that the radius of the quarter circle is 3 units, and angle DOB equals to 90 degrees. And we also know that line segment CD equals to 2 units, and DO, the radius of the quarter circle, equals to 3 units. And we also know that angle BCD equals to 90 degrees, and we want to find out the radius of the small circle. Okay. So, first of all, we defined the center of the small circle is point P, and then we join together points A and P by a straight line. and we join together points P and X by a straight line, so AP and PX are the radiuses of the small circle, and then we join together points P and B by a straight line, and we define the angle ABP as theta, and actually triangle ABP is a right triangle because of the fact that tangent BA is tangent to the small circle at point A, and AP is the radius. And we have the rule that tangent to the circle and the radius are always perpendicular to each other, so this angle is 90 degrees. So here the tangent AB and the radius are perpendicular to each other, therefore angle PAB equals to 90 degrees. So triangle APB is a right triangle, and we know that tangent theta in the right triangle APB equals to AP over AB, but we know that AP is the radius of the small circle, so tangent theta equals to R over AB. We multiply this equality by AB, and we got that the radius of the small circle equals to AB times tangent theta. Okay? So, in order to find out the radius of the small circle, we must find out the value of AB, and we must also find out the value of tangent theta. Then I proved that triangle PXB is congruent to triangle APB because AP equals to PX equals to R. Both those two sides are the radiuses of the circle, therefore they are equal to each other, and okay, we have to find out the value of AB and the value of tangent theta. In order to find out the radius of the small circle, we proved that triangle PBX is congruent to triangle APB because PX equals to AP equals to the radius of the small circle, PB equals to PB is the common angle, and AB equals to BX according to two tangents theorem. Two tangents theorem states that the length of two tangents from a common external point to a circle are equal. So according to the two tangents theorem, if from external point of a circle, that is to say from point B, we draw two tangents to that circle, that is to say tangent AB and tangent BX, then the lengths of those two tangents are equal to each other. That is to say AB equals to BX. So we actually proved that all the sides of triangle APB are equal to all the sides of triangle PBX, therefore those two triangles congruent to each other, and from the fact that those two triangles congruent to each other, we can derive that angle APP equals to angle PBX, and we know that angle ABP equals to theta, so angle PBX will be also equal to theta. So we derive this equality according to the rule that corresponding angles in congruent triangles are equal to each other. So those two angles are equal to each other because of the fact that triangle APB is congruent to triangle PBX. And then we extend that line segment CB and the radius DO until they intersect each other at point E. By extending those two line segments, we created two vertex angles, angle EBO and angle EBC are two vertex angles. I draw these two vertex angles again. The angles in the red line are the two vertex angles, and according to the rule, vertex angles are equal to each other. So angle ABC is equal to angle EBO. Those two angles are equal to each other. So actually we know that angle ABC equals to theta plus theta, that is to say to 2 theta. So if angle ABC equals to 2 theta, then angle EBO that equals to angle EBC to angle ABC will also be equal to 2 theta. So here angle EBO also equals to 2 theta. So this angle EBO equals to 2 theta, and we know that angle BCD is a right angle. Therefore, also angle ECD is a right angle, because angle ECD is the extension of CB, so it is the same angle. So angle ECD is a right angle, but angle ECD is a peripheral angle, and we have the rule that any peripheral angle that equals to 90 degrees rests on the diameter of the circle. So we have peripheral angle ECD that equals to 90 degrees, therefore it must rest on the diameter of the circle. That is to say, DE is the diameter of the quarter circle. So DE is the diameter, that is to say it equals to 2 times the radius of the semicircle. It equals to 2r, and if DO equals to r, then OE must be also equal to r in order to complete the size of DE to 2r. So DO also equals to r. Okay? So we also know that DE is the diameter, therefore it is a straight line. And we have a rule that the sum of the angles on a straight line equals to 180 degrees. So we know that this angle is a right angle, it equals to 90 degrees, plus the size of angle EOB must be equal to 180 degrees. Again, according to the rule that the sum of the angles on a straight line equals to 90 degrees, to 180 degrees, on the straight line ED at point O, the sum of the angles must be equal to 180 degrees. That is to say, 90 degrees plus angle EOD must be equal to 180 degrees. Here we subtracted 90 degrees from this equality, and we got that angle EOD equals to 90 degrees. So this angle is a right angle, and therefore triangle EOB is also a right triangle. And we focused on triangle EOB. We know that the sum of the angles in triangle EOB equals to 180 degrees. So 90 degrees plus 2 theta plus the size of this angle equals to 180 degrees. In triangle, the right triangle EOB, 90 degrees plus 2 theta plus the size of angle EOB equals to 180 degrees. Here we subtracted 90 degrees from this equality, and we got that 2 theta plus angle EBO equals to 90 degrees. We subtracted 2 theta from this equality, and we got that angle EBO, angle OEB equals to 90 degrees minus 2 theta. So this angle equals to 90 degrees minus 2 theta. And then we focused on the right triangle, the right big triangle ECD. We know that the sum of the angles in any triangle, and especially in triangle ECD, equals to 180 degrees. Okay, so the size of this angle plus 90 degrees plus the size of this angle that equals to 90 degrees minus 2 theta must be equal to 180 degrees. Okay, in the right triangle ECD, the sum of the angles is 180 degrees. We subtracted 180 degrees from both sides of the equality, and we got that the size of angle EDC equals to 2 theta. This angle equals to 2 theta. Then in the right triangle ECD, we know that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CD square plus CE square equals to DE square. Okay? CD square plus CE square equals to DE square. We know that this CD equals to 2, it is given us in the question, so 2 square is 4. And DE equals to 2R, R equals to 3, so 2R is 6. So DE square is 6 square, and 6 square is 36. So we got that 4 plus CE square equals to 36. We subtracted 4 from this equality, and we got that CE square equals to 32. We take a root out of this equality, and we got that CE equals to 4 times root 2. And then we know that in triangle, the right triangle ECD, times 2 theta equals to CE over CD. Times 2 theta equals to CE over CD, but we have already found out that CE equals to 4 times root 2, and CD equals to 2, it is given us in the question. So in total we found out that times 2 theta equals to 2 times root 2. Okay, times 2 theta equals to 2 times root 2, and we have the equality that the radius of the small circle equals to AB times theta. So we have to find out the value of tangent theta, but we have only the value of tangent 2 theta. So in order to find out the value of tangent theta from tangent 2 theta, we will use special trigonometric identity that tangent 2 theta equals to 2 tangent theta minus 1 over tangent square theta. And we already found out that tangent 2 theta equals to 2 times root 2, so we can substitute tangent 2 theta in the trigonometric identity by 2 times root 2. And we get this equality. We define tangent theta as x, and we got quadratic equation that root 2 x squared plus x plus minus root 2 equals to 0. We solve this quadratic equation, and we found out that x that equals to tangent theta equals to 1 over root 2, or tangent theta equals to 1 over root 2. X equals to 1 over root 2, so tangent theta that equals to x equals to 1 over root 2. Okay, so we know that tangent theta equals to 1 over root 2, tangent 2 theta equals to 2 times root 2, and the radius of the small circle equals to AB times tangent theta. So the only thing that is left to find the value of AB, and then we will know the value of the radius of the small circle. So in the right triangle EBO, we know that here tangents this right triangle, tangents 2 theta equals to EO over BO. Equals to EO over BO, but we know that EO equals to 3, and BO is BO, and we have already found out that tangents 2 theta equals to 2 times root 2, so we can substitute tangents 2 theta by 2 times root 2. Okay, and we got that tangents, we got this equality, and from here we found that BO equals to 3 over 2 times root 2. BO equals to 3 over 2 times root 2. And then we connected together points P and O. We created the right triangle, triangle APO. Then we extended the hypotenuse PO until it touches the two circles at point M. And actually PO equals to 3 minus R. So in the right triangle, triangle APO, according to the Pythagoras theorem, PA square plus AO square equals to PO square. Okay? Or AP square plus AO square equals to PO square. We know that AP equals to small r, PO equals to 3 minus r. So we put the data inside this equality and we found out that AO equals to the root of 9 minus 6r, and we already found out that BO equals to 3 over 2 times root 2. And the value of AB is AO minus BO. We found out the value of AO and we found out the value of BO. So we substituted AO and BO by their values that we have already found. And we found out that AB equals to this expression and tangent theta equals to 1 over root 2. The only thing that is left to do is to substitute AB by its value and to substitute tangent theta by 1 over root 2, and we will have the radius of the small circle according to this equality. Okay? So we solved this equality. We got to a quadratic equation that 16r squared plus 72r minus 63 equals to 0. We solved this quadratic equation and we found out that the radius of the small circle equals to 3 over 4 units, or 0.75 units. Okay, so the radius of this small circle equals to 3 over 4 units, or to 0.75 units. Okay, thank you very much.